All right, so now section 5.3, or 5.2, 5.2. 5.2, we're dealing with 3 equations and 3 unknowns. So somewhat similar, we're going to use the same 2 methods that we used. Actually, for section 5.2, we only use the elimination method, come to think of it. And this one is a little bit more involved. It's just more algebra, actually. Systems of 3 equations with 3 unknowns. So now, obviously, we're not talking about straight lines anymore. We're talking about 3-dimensional objects, so it's hard to picture on a 2-dimensional board. But really what we're talking about now is like planes. You know, like if, instead of a straight line, we have a 2-dimensional plane, P-L-A-N-E, not an airplane, but a plane in a 3-dimensional space. And the solution we're looking for is where those planes intersect in a 3-dimensional level. Again, it's hard to kind of visualize in a 2-dimensional board like this, but we don't really have to visualize it. We just have to do the algebra and come up with the solutions. So once again, actually in this case, we're not going to ever have no solutions or infinite number of solutions. We're always going to come up with a solution for these problems. So systems of 3 equations, 3 unknowns. Again, the first questions you'll see are checking whether a given, in this case we're looking at a ordered triple, x, y, z. This is called an ordered triple, as opposed to our ordered pairs that we were looking at when we were looking at lines, was just x, y pairs. Now we're looking at 3 dimensions, so we have x, y, z coordinates, which are going to be the answers to these problems. So for, again, first types of questions are you'll be given an ordered triple and asked, is it a solution to a certain system? So something like number 2 on page 537. We're given this system of 3 equations and 3 unknowns. yz equals 0, x plus 2y minus 3z is 5. That's our first equation. Second equation, third equation, 3x plus 4y plus 2z is negative 1. So notice, in order to solve for 2 unknowns, we need 2 equations. In order to solve for 3 unknowns, we need at least 3 equations. That's as far as we're going to go. Right? We're not going to go to 4 or 5. If you go, these obviously can go to more complicated systems. 10 equations, 10 unknowns. We don't want to deal with that, but there are ways to deal with those systems also. We're going to stop at 3 by 3. So number 2 says, is 5, negative 3, negative 2. So the question is 5, negative 3, negative 2 a solution to this system? I get that right? 5, negative 3, negative 2. All right, so again, it's always x, y, z. So just like before in section 5.1, we're just going to check to see if that x, y, z triple makes all 3 of these equations true. It has to make all 3 of them true. So equation 1, we get 5 plus a negative 3 plus a negative 2. Does that equal 0? Yes. So the first equation does check. Second equation has to check all 3. As soon as you get one that doesn't work, you're done. If that one wasn't true, then we're done. We say, no, it's not a solution. And there's no way to graph these and check for points of intersection, so we've got to be careful about our algebra. So second equation, x plus 2y minus 3z. We want to know, does that equal 5? So we got 5 minus 6 plus 6, and that does equal 5. So the second equation checks. So we go to the third, and we say 3 times x plus 4 times y plus 2 times z, and we want to know, does that equal negative 1? So we get 15 minus 12 minus 4. Does that equal negative 1? It does, right? So all three check. So yes, our answer is yes. It's a solution. Okay, so given a system of 3 equations, 3 unknowns, and asked if an ordered triple is a solution to that system, you plug that x, y, z into the first equation, you see it's true. You plug that x, y, z into the second equation, you see it's true. You plug it into the third equation, you see it's true, so yes, it is a solution. All right, so again, just like the last section, we're actually more concerned with finding solutions instead of checking whether given solutions are true or not. So that's our next step. And like we said, there's only one method here, the elimination method. So I'm going to have to go to the weaker chalk here. This is not the fancy chalk, the cheap chalk. I'll probably break it. We want to come up with a solution to systems here. So let's look at number 6. Oh, it feels different. It's way thinner. 2x plus y minus 2z is negative 1. That's equation 1. Equation 2, again, it's very important to line up your x's, your y's, and your z's if they're not already. That's something you want to do. In this case, they are lined up nicely for us. And it's a good idea to check that you didn't miss any signs or numbers or mix anything up, because it's very frustrating. If you just miss one sign, it screws up your entire work. So 3x minus 3y minus z, x minus 2y plus 3z is 6. Okay, so that's the question. Here's a system of 3 equations, 3 unknowns. We are asked to come up with that x, y, z that makes all 3 of these true. Okay, so this is sort of a lengthy procedure, so let's put out these steps. First step is you're going to choose 2 of the equations, any 2 of the equations. So you can choose 1 and 2, you can choose 1 and 3, you can choose 2 and 3. Those are your 3 choices. Choose any 2 equations and eliminate any one of the variables. Okay? So you look at this and you see if any are easy, like if there's a 2x and a negative 2x. That would be your obvious first choice, because then you could just add those together and eliminate the x's. But for the x's, there's no easy choice. For the y's, there's no easy choice. For the z's, there's no obvious choice. Okay, so it doesn't, so you got to make, this is a choice. You have a choice here. Any 2 equations, any one of the variables. So let's just go with equations 1 and 2, and we'll eliminate the y's. So what I got to do is multiply this by 3, so that I can add it to the negative 3y like we did in the previous 2 equation section to eliminate the y's. Okay, so you choose, in this first step, you choose any 2 equations and eliminate any one variable. So, different people are going to make different choices here. So one person's work may not look exactly like another person's work, but in the end, if you do it right, you'll get the same x, y, z variables. So I'm going to choose 1 and 2 and eliminate the y's. All right, so I'm going to choose 1 and 2 and eliminate the y. So I need to change equation 1 so it's 3y so that I can eliminate the y's. So I'm going to take equation 1 and multiply it by 3. Okay, so equation 1 multiplied by 3, I get 6x plus 3y minus 6z equals negative 3. Right? 3 times 2x is 6x, 3 times 1y, 3 times negative 2z, 3 times negative 1. I'm going to add that to the second equation and eliminate the y's. So I get 3x minus 3y minus z equals 5. Okay, so I add those together, eliminating the y. So now I have one equation with two variables. I'm going to call that equation 4, because it's a new equation. Okay? So that was my first step. I chose any two of the three equations and eliminated any one of the variables. There was no obvious choice here, so I chose 1 and 2, and I eliminated the y, and came up with a new equation in x and z. So now my second step, I'm going to repeat that procedure to come up with another equation in x and z. Then I'm going to have two equations in x and z, which we know how to solve from the previous section. We'll get that x and z. Once we know x and z, we'll come back here and solve for the third. Okay? So that was the first step. Second step, same as the first, except you have to eliminate the same variable, because you want your equation 5 to be also in x and z. So your second step depends on what you did with your first step. Since I eliminated y in the first step, I'm going to choose a different set of two equations. So I can't choose 1 and 2 anymore. So I can either choose 1 and 3 or 2 and 3 and eliminate the y again. So let's see, 1 and 3, let's do that. So then all I got to do is multiply this by 2 to eliminate the y again. Right? So second step, choosing 1 and 3, again eliminating y. Very important that you eliminate the same variable that you did in step 1. Okay, so now I'm going to let equation 1, I'm going to multiply it by 2 to get 4x plus 2y minus 4z and negative 2. I'm going to add that to the third equation, which is x minus 2y plus 3z and 6. Add those together, again eliminating the y, coming up now with what we'll call equation 6, or equation 5, sorry, equaling 4. So that's going to be our equation 5. Okay, so we came up in our step 1, we eliminated y and came up with a new equation in x and z. Step 2, we chose two different equations, eliminating the same variable to come up with a second equation in two variables. So now we're right back to section 5.1. We have a two equation, two unknown system. So let's go solve that. And once we solve that, we'll have two of the three unknowns, and then it will be easy to go back and solve for the third by putting those x and z into any one of these three original equations and getting our result. Okay. So now we've created a new system. So this is the third step. Third step is we've created a system of two equations and two unknowns. With two unknowns. Okay, so we'll use those same numbers, 4 and 5. So our equation 4 was 9x minus 7z equals negative 2, or positive 2, sorry. Positive 2, is that right? Mm-hmm. Okay, and 5x minus z equals 4. Okay, so now we just do exactly what we did in section 5.1. In this case, substitution wouldn't be so bad because we got the z sorted by itself. We could pull that over here and plug it in. Let's do that since mostly we're going to use elimination methods. So whenever we have a good opportunity for substitution, we may as well illustrate it. So here we're going to use substitution method. And I'm going to solve equation 5 for z. Solving equation 5 for z. If I bring z over here, that means I have to subtract 4, so I get 5x minus 4, right? Positive z, 5x minus 4. And then I'm going to plug that in to the other equation for z. So I get 9x minus 7z equals 2. Now I got my nice one variable equation, 9x minus 35x plus 28 equals 2. So we get negative 26x nicely equals negative 26, which gives us an x of 1. Right, so we took the first two steps, allowed us to form this system of two equations with two unknowns. We use either method from section 5.1. I chose the substitution method. I solved equation 5 for z, substituted that z with this in equation 1 to get one variable equation, solved that one variable equation. Now I have one of the three unknowns. Now I can plug this into either here, or even here, probably be easiest, right? I can just plug it in here to get the z. So I'm going to take this and plug it into my z equation and get z is 5x minus 4, so z is also 1. Now that I have x and z, I go back to any one of the original three equations and solve for the remaining variable. So let's come over here. So now I know, I told you I'd break that chart. I know x equals 1 and z equals 1, both positive, right? Yeah. Z equals 1. So now plug into either original equation, into any of the three original equations. I'll choose equation 1 just for the hell of it. 2 times x plus y minus 2 times z, I know equals negative 1. So now I have a one variable equation. I get 2 plus y minus 2 equals negative 1. So y is negative 1. So my answer to the original question, my answer is the ordered triple, x, y, and z. That's my answer to the question. And of course it's a good idea to check. 2 times 1 is 2, 2 minus 1 is 1, 1 minus 2 is negative 1, so that one checks. 3 plus 3 is 6, 6 minus 1 is 5, that one checks. 1 plus 2 is 3, plus 3 is 6, so we have no doubt that we got it right. All right, so that is an example of three equations with three unknowns. Obviously a little bit more work than the two equations. The first two steps are choices. Well, actually the first step is really the main choice. Your second step depends on the choice you made in step 1. In order to form the system of two equations with two unknowns, you solve that system of two equations, come up with those solutions. Once you have two of the three, you go back and put into any one of the original three to get the third equation. All right, and now the same thing that we had in 5.1 where you have to come up with the equations yourself. Let's just quickly look at one of those examples so that you can be prepared for that. So something like number 24. So I'm just going to change the sentences into equations. We won't go through the solving because it's exactly the same as what we just did. But let's look at least getting these equations correct. Page 537. All right, so it says the following is known about three numbers. 3 times the first number plus the second number plus twice the third. Okay, so changing English to algebra. Right? This is the main skill set involved in these questions. So for 24, you got 3 numbers, you got x, y, and z are 3 numbers. There's the sum, or sorry, following is 3 times the first number, so equation 1. 3 times the first number plus the second number plus twice the third number is 5. So there's your first equation. Once you get the 3 equations, it's no different than what we just did. Coming up with the equations is the only additional part. Then you look at the second sentence. It says, if 3 times the second number is subtracted from. Now this is where the main mistake in these comes. The main word there is from. You're subtracting from something. So this says 3 times the second number, so 3 times the second number is subtracted from something. Many times people will make the mistake and do this, right? 3 times the second number is subtracted from, that's not subtracted from, right? This is being subtracted from this. So this is the key, is getting these sentences right. 3 times the second number is subtracted from the sum of the first number and 3 times the second. So 3 times the second number is subtracted from something. It's subtracted from the sum of the first number and 3 times the third. Okay, so that is the second equation, and that equals 2. Okay, so coming up with the correct equations is really the main part, because once you come up with the correct equation, and in this case, again, you want to line up the x's, the y's, and the z's, and then we're just back to where we were before. We need a third equation, so a third sentence says, if the third number is subtracted from, again, so third number subtracted from something, 2 times the first number and 3 times the second. 2 times the first number and 3 times the second. So you got to be careful about translating these sentences into English. And that equals 1. All right, now just switch this to say x minus 3y, so you can line up the x's, the y's, and the z's. And then you solve this exactly the same way that we did the previous one. I'm not going to go through that since we want to save a little bit of time. You can try this one as practice again. Kind of rewrite this as 3x plus y plus 3z equals 5. Just change the second equation so that we have the x's and y's lined up. Equals 2 and 2x plus 3y minus z equals 1. And then you want to solve that system again by going through those steps. Now this one, first step you would see is a little more obvious since we got a plus and a minus 3y. So you can do that as the first step, have x's and z's, and go on your merry way. Okay, that's good.